think the recording has started. So welcome to the fourth problem solving session in this course, Fundamental Algorithms, Design and Analysis. So this is the first question, as you can see on your screen. Dijkstra's algorithm is used to solve what problems? Any guesses? So we have seen Dijkstra's algorithm in this week, and it was used to solve some problem. So is it network lock problem? Or is it the single source shortest path problem? Or is it the all paired shortest path problem? Or is it sorting? So do you remember Dijkstra's algorithm? Anybody? Okay, so let me write down this pseudocode for Dijkstra's algorithm. So what is the input? So the input is a graph. Graph G and a set of weights on the edges and a source vertex S. The objective is to compute something which will be clear once we write the pseudocode. So it is going to work on a graph and there are weights on the edges. Okay. Sorting is probably immediately ruled out. So initialize single source. So with respect to the graph G and the source S, initialize single source. So what does that do? So that sets the distance from the source to 0 and distance from every other vertex to infinity. Then you create this set S and initialize to the empty set. The video if I'm okay. Maybe I would slightly. And then you have a Q, which is initially the entire vertex set. And then you have a while loop. And the while loop runs as long as the Q is non-empty. So what does we do inside the while loop? So we extract the minimum element from the Q. So when we initialize the single source, we also set the values corresponding to these vertices, the shortest path estimate. So single source shortest path. So source has value 0 stored in it, and every other vertex has infinity stored in it. Right. And then once you extract it, you add that to the set S. So this is a set for which we have found the shortest path distance. And then for each vertex B, the adjacency matrix of U, the adjacency list of U. What we do is we update the shortest path estimates. So what we call relax or decrease key. Okay. So we'll say relax via that edge UV. So like if E is reachable, then the edge from U to V. Okay. So if E is reachable, we can say distance 10 from the source. then what is relax too? So there is an edge W, WE. So that must be is reachable with cost 10 plus WE, right? From the source. Because it is reachable with cost 10. So this is an example of it. Instead of W is take 4 so it is reachable with a cost of 10. Then if you take the HU to V further, then you will be able to reach V from S at a cost of 10 plus V. You see what is relax already. So now you can tell me that what is this algorithm doing? What is the use of this algorithm? Is it all place ordered path? Is it single source of this path, or is it network log? Any thoughts, any ideas? You can also write in the chat box. Well, clearly, since we're still not getting here, not listening, but anyway, so it's a single source shortest path that this algorithm is solving. This is the answer. So let's move to the next question. It's again on Dijkstra. We'll have the algorithm on view. So this is question number 2 for today. So the maximum number of times decrease key operation is performed. In Dijkstra's algorithm will be equal to what? So decrease is implicit and relax. So if the present estimate is poorer than the estimate that we are going to get via this edge, then we update the estimate. That is a decrease key operation. So we implicit here. Implicit. Decrease key operation. So view it out. Look at the pseudocode for some time. The options are also simple. Total number of edges, vertices, total number of edges, number of vertices minus 1, number of edges minus 1. So look at this algorithm. So get it and try to get an upper bound on the relax operation, that is the decrease key operation, which is implicit here. No clue. Give some time. Okay, so I will tell you the answer. So when does relax observation take place? When you have identified the vertex with the monolithic view, and then you are looking at all its neighbors, all the neighbors, and you relax the edge in comma V. So there's a weight of UV, so you relax V with respect to U if the estimate of U is base poor. Okay. So relax observation is taking place for every edge essentially, right? Now, how many edges are there? That many times relax observation take place at the most, right? So therefore, the total number of edges is what we should answer. This is the correct answer. Okay. Any doubts? I'll mark this as the correct answer. If you're not able to solve, if you're not able to see the screen, then please let me know. So for some of you who have joined, now I'll show the first question. You can take a look at it. So here we were basically asking that what is the use of Dijkstra's algorithm, for what problem we use the Dijkstra's algorithm. And we said that it's a single source shortest path problem, and we also looked at the pseudocode. All right. Fine. So let's move to the next question. So this is question 3. Consider the following statement. A DFS has a back edge. If a DFS has a back edge, it does not imply G has a cycle. So you are running the depth first search on a graph G, and you encounter a back edge, back edge, but that does not imply that G has a cycle. Okay. And the other statement is a subpath of the shortest path is the shortest path. What is a subpath? So a path is a set of vertices. The adjacent vertices are connected. So every vertex has to be 2, except the last end vertices, which have to be 1. Subpath is a subset of vertices within the path, and the subgraph induced by them. So we're saying that subpath of shortest path should also be shortest path. So these are the two statements that we have. We have to decide that which of them are false. In many cases, so we do a DFS. On a graph. So the DFS can be done on a graph, whether it is directed or undirected, does not matter. But you start the DFS from some vertex. Let's call that the source vertex. So once you are doing the DFS, so basically the source is the root of the DFS tree, and then you explore one of its neighbors. Let us say V1, and then there are other neighbors of S, but you don't explore them immediately. We explore one of the neighbors of V1, let us say V2, and so on. So if at some point you reach a vertex that doesn't have any neighbors, then you fall back. Or if let us say it so happens that it has a neighbor, but that neighbor is already visited, then you have a package. Okay. So does it imply that if you encounter a package during the DFS traversal, that means that G has a cycle? So what do you think? Are you following me? So if you have encountered a cycle, rather sorry, if you have encountered a package, so that package is from some vertex to a vertex that you have already seen before. And a vertex that you have already seen before, from that vertex you have followed a path to reach this vertex from which you have the package. So therefore, this path as well as this package together forms a cycle. Isn't it? The existence of package immediately implies a circle, a cycle in the graph. So this statement does not imply G has a cycle is false. So one is definitely false. So we have to now check what about two. So let us say this is the shortest path between two vertices. Let's say P1 and P2. And there is, you know, edges are weights. So now if it so happens that if you consider the subpath in the shortest path, and this subpath is between one vertex, let us say E1 and another vertex U2. So if this is not the shortest path between E1 and U2, then there is a shorter path between E1 and U2. Right. So what it would imply that if you start from V1 and take this shorter path and then go to V2, then the length of this path is going to be even smaller than the length of this shortest path, which is a contradiction to the definition that we have shortest path between V1 and V2 this way. So this means that the shortest path have this property that every subpath of shortest path is also a shortest path. So therefore this is correct. This is true. Isn't it? So one is true, two is false. So this is not correct. This is not correct. This is not correct. This is answer. Okay. Is that clear? Any doubts? Great. We are in Q4 to this session. So let me read the question. Consider the complete or rather a complete binary tree with 7 nodes. How many nodes? 7 nodes. Okay. Let A denote the set of first 3 elements obtained by performing breadth first search starting from the root. So you have a complete binary tree and you are doing this breadth first search and you found 3 nodes. The first 3 nodes is what they investigate. And these first 3 elements that we obtain by DFS on this tree, we denote them by the set A. And the set B is what? B denotes the set of first 3 elements obtained by performing a DFS starting from the root. So we want to know that what is the cardinality of the set A minus B. So this could be a unique number. So I would encourage you to give it a thought for some time. So first, we'll draw one complete binary tree. Complete binary tree on 7 nodes. Complete binary tree means every vertex has 2 children, right? This is a complete binary tree. And having how many nodes? 7 nodes. Now we think about it. And remember, BFS means you first explore the neighborhood of a vertex. And DFS means you explore only one neighbor of a vertex and then you explore another neighbor of the recently discovered vertex and so on. So let me draw a binary tree for you. Rather, a complete binary tree for you. And now you can try to think. It has 7 nodes, and you are going to perform BFS and DFS on it. So when you do BFS, then you encounter some vertices. You consider the first 3 vertices and put it into A. When you do DFS, you encounter 3 vertices and put them. The first 3 vertices, you put them into B, and then you take the set difference A minus B, and then you take the cardinality of that, and that is going to be the answer. So now you can do it yourself. Fine, so let me help you. First, we'll do PFS. We start at the root. We explore its neighborhood. There are 2 children with complete binarity. And then we don't go further because we have seen 3 elements already. So A is nothing but, in this case, the elements 1, 2, and 3 in a set. Now we do, what shall we do? Now we shall do DFS. So 1, take one of its neighbors. 2, take one of its neighbors. Okay. So this forms a set P. This is like 1, 2, and 5. So what is A minus B? Which element is in A minus B? So A has 1, 2, and 3, and B has 1, 2, and 5. So 3 is contained in A but not in B. So A minus B is the singleton set consisting of the element 3. So it's cardinality of elements. So only one element. So what will be the complete binary tree, this is what is going to happen. Because the BFS will take the root and two of its children, and the DFS will take the root one of its children and one of its grandchildren. So the root and the child, one of its child will be common in both the BFS and DFS, the first three elements. Only one element which will be there in DFS and not in BFS, and similarly there will be one element which will be in BFS, which is one of the children of the root, which will be in BFS but not in DFS, because it's a complete binary tree. Right. So therefore the answer is going to be one. Always. Is that fine? If you have any doubts, you can let me know. Okay, so let's move to the next one. So this is question 5 for today. This is question 5. I will let you read the question. So again, we're doing BFS. So what are we doing? We started BFS on a binary tree, beginning from the root vertex. There is a vertex T at a distance 4 from the root. So let's say this is the root, and at some distance, in fact, we have been told it is 4. There is a vertex T. At 4 distance, there is a vertex T. So P is the nth vertex in the BFS traversal. So if you do the BFS traversal, it does not know the nth vertex. Then what is the maximum possible value of n? That means if you do the BFS, then how many elements will show up before T, including T? That is the question. So now we're going to think about it. So you have options 15, 16, 31, and 32. We are doing BFS. Why 31? Ravi. So you have to identify that what is the maximum value of n. That means how many vertices have come before T plus T, because you want to identify what is the serial of T, what is the serial number of T. If you do this DFS and you want to identify what is the maximum serial number of the node T. So let's get started by enumerating. So let us say We're doing BFS. So first element is numbered 1. And we are going to begin by 1. The first element that we encounter, that is the root vertex. So this is the root. And if we want to maximize the number of elements before t, we would like to have a complete binary tree. Instead of binary tree, we would like to have a complete binary tree. So we'll have 2 children of 1. Again, for 2, we'll have 2 children. Again, for 3, we'll have 2 children. So once we're doing this BFS, so we're exploding in this order. Then 4 has 2 children. So in this level, how many values? Each of the 4 nodes in the previous level have 2 children. In this level, we have 8 nodes. But every node is at distance 3 from the root. We have to go 1 more level down. So we have this level. In this level, how many nodes do we have? So 8 nodes, each of them having 2 children. How many do we have? 16 nodes. So it is in this level at a distance 4 from the root. Now, if you want to maximize the serial of t in the BFS, then you would keep it at the right here. So what will be its rank or rather serial? So 1 here, 2 gone here, 1 plus 2 plus 4 plus 8 plus 16. So this comes out to be what? We have to add all these things. Yes, 31. You're right. So any doubts, anybody? Move to the next. So this is the 6th question for today. Question 6. Which of the following is a linear constraint? What is a linear constraint? So linear means degree 1. So basically, you can think of constraint as an inequality. Like in this case, each of the options is an inequality. So we'll just say inequality. Which of the following is a linear inequality? So, but linear inequality means so every term has degree at most 1. So that is the definition of linear inequality. So, right. What do you get this term? This is x to the 1 plus y to the 1, n to y to the 1. So the combined degree is 1 plus 1. This is degree 2 term. So this is ruled out. This is degree 3 term. This is degree 4 term. This is degree 1. This is degree 1. This is all degree 1. So this is linear for sure. This is degree 1. This is degree 1. But this is degree fractional. So this is not linear. This is fractional. So degree is less than 1. That's 2. So I would rather say something else. This is a degree 0, 1, and degree has to be non-fractional. Let me verify what I said. The function has to be linear, okay? Yes, it can be either 0 or 1. That's why this is also ruled out. There is fractional degree. Okay. Any doubts? Question 7 for today. How many times? Just a second. Yes, so how many times the for loop in the Bellman-Ford algorithm gets executed? So you see the Bellman-Ford algorithm this time. You don't recall Bellman-Ford, let me open that for you. This I'll write Bellman-Ford for you. So it takes a graph, weights on the edges and a source vertex. So first step is to initialize the single source with respect to S. Second step, there is a for loop that runs from 1 to the number of vertices minus 1 times, and every time you are going to relax each edge in the graph. The relax operation we have seen already. And for each edge, you comma V in the graph to check if you still can make further relaxations. If that is the case, then you say that look, we cannot find the algorithm for this one. So yeah, I need to think about it. We'll take a break, short break. We'll be back into 3 minutes. Okay, so we're back again. I hope you had a chance to think about it. Okay, okay, I can see there is one answer by Ravi, option B, that is correct. So as you can see that you run this for loop, you get begin minus 1 times. So this for basically, and number is 6. And then after that, what do we do? We try to relax every edge once again to check whether there's a negative cycle. If there's a negative cycle, then taking that cycle, shortest path can be even further reduced. So basically, the shortest path is not even verified. There's a negative cycle. That is also done. So basically, this for loop is run in minus 1 time. This for loop is run once for every edge. So if you consider this for loop, that is b minus 1. If you also consider this additional iteration to detect negative cycles, then the answer would be B. It depends on how you uh, interpret your answer. So the answer that NPTEL has provided is this. For this, for the answer is this. So I'm going to also argue about this idea. But this is only to detect negative cycles, so I'm going to escape this step which somebody likes. And so it is known that the input does not have a negative cycle, and this loop is not triggered. Okay. You can ask if there are any doubts on this question, then we move to the next question. Do you have any doubts? Okay. I got my point. Great. Now, question about efficiency. Question 8 for today. Consider the following statement. Dijkstra's algorithm is more efficient than Bellman-Ford algorithm. So we have to say what is the running time of these two algorithms. So what is the running time of Dijkstra? What is the running time of Bellman-Ford? So Bellman-Ford, as you see, this loop runs a minus 1 times. And we're relaxing every edge. This loop runs e times. So overall running time sort of be, but Dijkstra will know that order Dijkstra is sufficient even if we don't use fancy data structures. So E can be how much in terms of P? So in the first case, we can implicate vertices that can be image. So we choose 2. That is order B square vertices edges are possible. In the worst case, it is order B square. So this could be as large as order P cube. So which one is faster out of Bellman-Ford and Dijkstra? Of course, Dijkstra is faster because it is faster, then it is more efficient. Right? Isn't it? The faster the algorithm is more efficient. What do you say? Why do you think this false? False. A is proportional to B square, exactly. A is proportional to B square, that is why Bellman-Ford has runtime order BQ. right? So Dijkstra is order p square only. So which one is faster? Which one is more efficient? Dijkstra. So what is the statement? Dijkstra's algorithm is more efficient. Dijkstra's algorithm is more efficient than Bellman-Ford. Then is it true or false? Correct. It's true. Any doubts on this? Anybody? Yes, other than Ravi, nobody has a doubt. No? All good. Okay. So to my second last question. So this is about Floyd-Warshall algorithm, which is what approach is being followed in Floyd-Warshall algorithm. What is the approach? That's all. That is a simple question. Is it greedy? Is it a dynamic program? So you know what is greedy. So in the greedy, you solve a problem by making choices that seems right immediately. So you are greedy. So in dynamic programming, you divide the problem into sub-problems and solve the sub-problems. And then combine the solutions to the sub-problems and find a solution and output that solution. So in linear programming, you will write the linear programming relaxation and then doing some more step. So you have three options, and if you think that none of these three is true, then you go with none of that one. So let me write down the pseudocode for cloud version so that you can recall it. Then we will be able to answer this question. So remember that, okay, let's let me first write down. We'll talk about it. What does it takes? Weight matrix and so I'll write it down first. So what is the use of Floyd version? That is the first question. So what does Floyd version do? It finds the all paired shortest path. So, that means between every pair of vertices, it finds the shortest path. So what we can see here is that what we're doing. So n is the number of vertices in the graph. For just a second. Run this loop from 1 to n. Uh, what is W initialized to? Anyway, before that, there are three for loops nested. If each of them runs n times, and what this step is essentially doing. So Dijk is a distance from node I to node J, where you have used intermediate vertices between the numbers 1 to k only. You haven't used other vertices. There are any vertices anywhere. You use vertices among 1 to k to go from 1 to j. And then with that constant, what is the distance, minimum distance between I and j? So this they have divided into two parts. One is using the vertex k itself. So you're moving from I to k via I to j via k. So in that case, what will happen? That first you check that okay, using vertices from 1 to k minus 1. In what cost I can go to k. So you will go from I to k first, and you are using vertices from 1 to k minus 1 only in between. And then you move from k to j. Again, you are using vertices from 1 to k minus 1 only. So these terms mean that. So this is one cost. The other cost is you do not use k at all. So you have found that there is another path from I to j that doesn't use k. So and now then in this path also you have vertices from 1 to k minus 1 only. So this is the other part. So one is whichever is minimum, you take this. So basically you have divided the problem into two subproblems. One is a subproblem where you have used the vertex k as an intermediate vertex to go from I to j. The other is a subproblem where you have not used k. So you use vertices lying in 1 to k minus 1 only. And then you have defined this recurrence. What is the distance from I to j if you use vertices from 1 to k? Basically, it is like a recurrence where you find something with respect to the subproblems. Then what kind of algorithm is this? Standard program, correct. Because you have divided the problem into subproblems, and then you have written a recurrence with respect to the subproblems to find the solution of a larger. This recurrence itself is telling us that it is a DP. Dynamic programming in short is also called DP. Linear programming is also called LP. Okay. It's not 3D. Is that fine? Any questions? Okay. So I'm going to move to the last question. Okay, so can't you say we'll give you to it? There is no step where we are using greediness. So we are just comparing these two values. And we are trying all sorts of possibilities. So we're trying it, okay, so out of all these paths within I and J, that does not use the vertex K, which one is minimum? So we're trying all sorts of possibilities. And among all these parts that go from I to K, and we're not interested about what is minimum. We try everything out. Instead of, so when we are greedy, we don't want to try everything out. We just pick the one which seems right immediately without trying everything out. Then we're trying everything out. We're enumerating everything. And out of them, we're eventually finding the minimum shortest thing. But since we're trying everything out, explicitly we're doing calculations. In fact, we're forming a table. That is the reason it's not greedy. So this is last question of today. So what is the time complexity of Floyd-Warshall algorithm to calculate all your shortest path in a graph with n vertices? So we'll look at the algorithm. So you have n vertices in the graph. You're performing this algorithm. It has multiple for loops, and you want to find what is the running time. So the for loops essentially are going to decide what is the running time. So how many for loops? This is one for loop. This runs n times. There is another for loop that also runs n times. Within this, there is one more for loop that also runs n times. But within this loop, what are we doing? We have two quantities which we have looked up from the table. We have formed a table D, and we're comparing these two quantities and taking the minimum. So these tasks, finding the minimum of two quantities, because this is just comparing. This is going to take constant time. Because we have found the table, remember, the table D we have found. Okay. So D is a new crossing matrix, basically. From the matrix, we are looking now. What is the value of these two things? So this task is not heavy. It's a light task. Right. So this takes only constant time. This task. So therefore, the combination is here. Run this n times. N times running in each of these n iterations. And this entire n cross n squared things is done again n times. So n. How many? 3 loops, n cube. The innermost loop is only constant time. And that is the reason we don't worry about it. This order n cube into order 1 is order n cube. Okay? Get understood. Fine. Great. So right now, we are at the end of this session. So the last session, I mean not last session, there was some last question in which we were stuck and we could not solve it. So we're going to do one extra session, 1 hour session for doubt clearing. So in that session, in about 10 to 15 minutes, I'm planning to revisit that question. Is that fine? Okay, got the answer at 64. Great. Yes, you can explain. So let's do one thing. Let's open that. Yes, this is a question we had. So the number of books in which the numbers 1, 2, 3, 4, 5, 6, 7 can be inserted in an empty line research tree such that the resulting tree has height 6 is found. Every step we have two choices to select. To get the highest or lowest value out of the given list. Okay. So like we are saying in the following. So in for the first node we have two choices, 1 or 7. Now let's say we fix 1. And here we have two choices, 2 and 7. Finally will be so we'll fix once 6 nodes are fixed, the last thing is determined already, right? Okay, therefore in every step we have two choices. Last step you don't have any choices because that number is the last remaining number that is already determined. The 2 to the power 6. That is correct. Very nice, very good. At every step we have two choices to select either the highest or the lowest value out of the remaining list. That is to say, very good. Very good. That's how it is 63. Very nice. So what we are going to do? What I am doing. 64. So in the next session we'll have one doubt clearing session. If you have any doubts, you can ask me. I think this is a short course for this, so I think the last session is going to be next week. So I think that is the end of it today. If you have any questions, I'm here in another 2-3 minutes, so you can ask me. So it is 7:13. At 7:15, I'll close. If you don't have questions, if you have questions, we can continue. Yes. Anybody is saying anything? Manjunath is not here today. He also had got the answer 64 for that question, that day itself, which I looked up later. He had written on the chat. So good job, Manjunath. And also Ravi. So okay, I think you don't have any more questions. So let us conclude today. So I'm going to stop recording. Good night.